In the case of the ramp walls, its own self-weight will be what resists global overturning. In the diagram, we have the active earth pressures from the rock fill and the grout compounding. See how they add together. We can take the very same equation used for active earth pressure, P equals 1/2 Ka times density times the height squared times W, where W equals 1 meter, because we're taking this per meter along the wall. This time, however, the density and the coefficient of active earth pressure will vary from the values we used for soil, which you may remember for a level backfill, Ka is 1 minus sine phi over 1 plus sine phi, and for soil that phi was 30 degrees. However, for the rock fill or angular rock fill, we'll take a phi of 40 degrees, and for the grout or slurry mix, we'll take a phi of 20 degrees. And this leaves us with the following, given those phi values and those gamma values, this leaves us with the following Ka values. And you remember these density values come from the previous lecture on abutment fill density. So we have a Ka for the rock of 0.22 and a K for the grout as 0.49. As a quick sanity check, we know that loose rock has a larger angle of internal friction. Therefore, we'll have a smaller K value because it produces less lateral forces. Another quick check will show us that this will also never work for a 3.5 meter tall wall. And that's okay, because it's unlikely that a 3.5 meter wall will be filled completely in a day, and it shouldn't be. It's more likely that the ramp wall will be built in lifts in tandem with the fill, making it easier to access and build the wall as you go up. In fact, approach ramps should be filled in 30 centimeter lifts according to the EIA Bridge Binder Volume 3 for field operations, with a maximum of 3 lifts or 1 meter, approximately 1 meter of height gained per day. And this is because of the following calculation. So the worst case scenario occurs along the 30 centimeter wall because it is the lightest. We'll assume 0 tensile capacity at the connection between the walls, and we'll check overturning. We'll also distribute the load by volume, taking the EIA Bridge Binder assumption that 15% of the volume of the rock wall is made up of grout. So here in our calculation, we have the force from the rock written out with the variables for rock fill to be 1.4 kilonewtons per meter of wall, and our force from the grout to be 0.63 kilonewtons per meter of wall. And we're letting our total height be 0.9 meters because we're doing 3 lifts of, we're assuming we're doing the maximum 3 lifts for 1 day being applied on this wall. And we can calculate our overturning moment and our restorative moment. Our overturning moment is just going to be the rock and grout forces multiplied by that h over 3, because they're a triangular distribution. Like we discussed in previous lectures, their resultant is going to be at 1/3 height from the bottom of the triangle. And our restorative moment is just going to be the self-weight of the wall. And we're taking all of these forces at point A that I've written on the diagram. And we're summing for our overturning moment and our restorative moment. We get a factor of safety of restorative moment over overturning moment of 1.37. And we're going to check this against our factor of safety of 1.25 because this is a temporary construction condition. So this establishes our maximum of 3 lifts or 90 centimeters of ramp wall fill per day without further analysis into the tensile strength of fresh mortar, using a reduced safety factor of 1.25 for temporary conditions. As you may imagine, we can evaluate this assumption a little further if we needed to fill more than 1 meter in a day, and we can do a calculation for what that tensile capacity between the various lifts of ramp wall or various sections of ramp wall would be so that we can get a little extra capacity resisting overturning.